Dear students, today my topic is enantioselective crossed aldol reaction. Now, as all of us we know, any enantioselective reaction can be successfully achieved by applying any one of the four important strategies. What are the strategies? Number one is by using chiral substrate, number 2 by chiral auxiliary, number 3 by chiral reagent, number 4 by chiral catalyst. Now let us move to our discussion where our prochiral substrate RC double bond O CH2 CH3 will undergo the reaction with the chiral auxiliary S-proline. Now let us introduce our prochiral substrate. This substrate contains enantiotopic hydrogens next to the C double bond O. Adjacent to the C double bond O there is one CH2 group. The two hydrogens of this CH2 group are enantiotopic as this carbon satisfies the pattern CABXX type. Now in addition with this, our prochiral substrate also contains enantiotopic phases. That C double bond O of prochiral substrate are enantiotopic. One phase is the V phase and another phase is the psi phase. Now this ketone will undergo the reaction with the chiral auxiliary S-proline. Now this proline is amino acid and naturally occurring. Now coming to the reaction between substrate and chiral auxiliary, there will be the water elimination and we will be getting the imine. Now this imine will undergo the tautomerization and we will land up into the enamine. Now this enamine is the species where prochiral substrate is covalently attached with the chiral auxiliary naturally occurring S-proline. Now let us talk about the stereochemistry of enamine. That enamine double bond can exist in the Z form or it can exist in the E form. Now thermodynamically more stable is the E-enamine where the nitrogen has the first priority and the R has the second priority. The opposite side of the double bond, methyl has the first priority and the hydrogen has the second priority. So the first priority groups are oriented in the opposite side, so therefore this enamine is the E-enamine. In aldol condensation we know that if we proceed through the carbonyl group, if it undergoes the reaction with the E, then we will get the anti-product, whereas if that carbonyl compound undergoes the reaction with the Z, then we will end up into the syn product, so that is the syn and the anti-diastereoselectivity. Now as because in our case we have E-enamine, then E-enamine when it will undergo the reaction with the benzaldehyde, then we are supposed to get the anti-product as a major product over the syn product. And this two chiral centers which are obtained due to this crossed aldol condensation where the methyl will be below and the OH will be above the plane. Why? Because the OH and the carboxylic acid will undergo the hydrogen bonding. Now after this we are reaching to the last step where we have to remove the chiral auxiliary by doing the hydrolysis. So if we do the hydrolysis, that C double bond N that will undergo the breakage and we will land up into the final crossed aldol product which does not contain the chiral auxiliary, and the two chiral centers which are obtained, they have the anti-geometry. Now we can apply this to the next substrate, that is the cyclohexanone. Just like in a previous case, this cyclohexanone is also one prochiral molecule, and it adjacent to the C double bond O of cyclohexanone, we have the CH2 group, and the two hydrogens of this CH2 are enantiotopic, as it comes under CABXX type. And what is the difference between cyclohexanone and the previous example is that C double bond O of this cyclohexanone has the two homotopic faces, whereas in the previous case the C double bond O also has the enantiotopic faces. But now coming to the reaction, means this is our prochiral substrate which has the enantiotopic CH2 adjacent to the C double bond O, will undergo the reaction with the chiral auxiliary S-proline and will get the E-enamine. Now this will undergo the reaction with the RCHO, and we will be getting, as because the this is through E geometry, enamine has the E geometry, that aldol product what we will be getting, that is a beta hydroxycarbonyl compound, will be having the anti-orientation, and this anti-orientation also we will be having, that is OH will be having the above the plane orientation, and the that alpha carbon will be having the below the plane orientation. And after removal of the chiral auxiliary by hydrolysis, we will be getting our final desired product with the E geometry. Now in a exactly similar way, if we proceed for the third example, by using the chiral auxiliary S-proline, we will land up into the major anti-product, and out of this anti-product we know that there are two anti-products are possible, but out of those two enantiomers we will be having a specific enantiomer as a major product, that is because of the intramolecular hydrogen bonding between the chiral auxiliary carboxylic acid and the OH of the at the beta position. Now let us change our strategy for enantioselective crossed aldol reaction. Now we are going to take the help of another chiral auxiliary, which is nothing but David Evans oxazolidinone. Now in case of chiral oxazolidinone, there will be some groups at the chiral center, and depending on the orientation of those groups at the chiral center, there will be some facial biasness. Suppose at the chiral center phenyl group is above the plane, then phenyl group will make the above the plane sterically congested. If the phenyl group is below the plane at the chiral center of oxazolidinone, in that case this phenyl group will make sterically congested the alpha side, means the below the plane. Now let us go to the actual reaction, where the step 1 is the covalently we have to attach David Evans oxazolidinone with our prochiral substrate acid chloride. Here it is, we have taken the propanoyl chloride. Now what David Evans oxazolidinone we have used here at the chiral center, isopropyl group is above the plane. So when it will undergo, first it will undergo the elimination of HCl, and chiral auxiliary prochiral substrate, they will be attached covalently. Now when this chiral auxiliary attached substrate will undergo the reaction with the boron complex in presence of diisopropyl ethylamine, DCM as solvent, and the temperature at 0 degree centigrade, then we will be getting the Z-enolate, because we know in presence of boron complex Z-enolate is the major product over the E-enolate. We know in case of aldol reaction, if the reaction proceeds through the Z-enolate, then we get the syn as a major product, means the beta hydroxycarbonyl compound what we will be getting, that will be having the syn stereochemistry at the adjacent chiral centers. Now, as because in our case we have prepared the Z-enolate. Now, this Z-enolate, when it will undergo the reaction with benzaldehyde in the next step at a very low temperature -78 degrees centigrade, in that case we will be getting the syn as a major product. But the syn means the two groups may be above the plane or two groups may be below the plane. Now, whether two groups will be below the plane or two groups will be above the plane in the final product, that will be decided by the big group, means in this case the isopropyl group of oxazolidinone. Now, as because in our case that isopropyl group is oriented beta, means above the plane, so the syn product what we will be getting, the OH and the methyl newly generated chiral centers will be having the alpha orientation, means the methyl and the OH will be below the plane because the isopropyl group of oxazolidinone is above the plane. That will be the major syn product, and the minor syn product will be having OH and the methyl will be above the plane, just have the syn orientation with respect to isopropyl group, means the isopropyl group, methyl group, OH group, these all will be oriented in the same side, and that is the beta side, means above the plane, and this will be the minor product because there will be steric crowding between isopropyl group and the methyl group. Now, after getting this diastereoselectivity, we can separate these two diastereomers, and after separation of these two diastereomers, we can remove the chiral auxiliary by hydrolysis, and we will be getting the major enantiomer where the hydroxy group at the beta position and the methyl group at the alpha position adjacent to the carboxylic acid, they will be having the alpha orientation, whereas the minor product will be having the beta orientation for the OH group at the beta position and the methyl group at the alpha position with respect to carboxylic acid. Now let us go to the another variation in crossed aldol condensation. If we take the two components of the aldol reaction, means the enolate and the carbonyl compound, if both are chiral, then the stereoselectivity can be increased than the reaction where the one component is chiral. This case is called as the matched aldol reaction. And if the stereoselectivity is decreased in the reaction from two chiral components than the reaction from one chiral component, then that is called as the mismatched aldol reaction. And where the two components are chiral, in general those reactions are called as the double stereodifferentiating reactions. Now, as because we are trying to apply this concept in case of the aldol reaction, so this is an example of double stereodifferentiating aldol condensation reaction. Now, in order to understand whether it is an example of matched aldol reaction or mismatched aldol reaction, first we have to perform one aldol condensation reaction where one component is chiral. Now, we are taking the chiral aldehyde and the achiral Z-enolate. Now, in case of chiral aldehyde, the alpha carbon, means the next to the aldehyde carbon is chiral because that carbon is attached with the four different groups. One is aldehyde, second one is oxygen, third one is CH2, and the fourth one is hydrogen. And if we give the priority to that chiral center, oxygen is the first priority, aldehyde is the second priority, CH2 is the third priority, and hydrogen is fourth priority, and hydrogen is oriented below the plane. So here the chiral center has the R absolute configuration. Now this chiral aldehyde will undergo the reaction with one Z-enolate. Enolate is undergoing the reaction with the chiral aldehyde. So it is expected that we are going to isolate the syn product as a measure. Now which syn product will be the measure? It depends on the orientation of the group at the chiral center. So as because the chiral center oxygen is above the plane, so therefore the two methyl group and the OH group at newly generated chiral centers at the alpha position and the beta position, they have the alpha orientation, means they are preferring to go to the below the plane. So that is giving the measure product whether we are performing this reaction in THF or we are performing this reaction in tetramethoxybutane solvent. In first case the ratio is 4.3:1 and in the second case the ratio is 5:1. Now let us consider the crossed aldol reaction where two chiral components are participating. Now when the two reactants are chiral, in that case depending on the percentage of the major product, we need to understand two names. One is matched aldol reaction and another one is the mismatched aldol reaction. Now let us discuss that what type of reactions are called matched aldol, what type of reactions are called mismatched aldol. Now before going to explain these terms, I would like to mention these terms are exclusively based on the percentages of the major product in comparison with the percentage of the major product where the only one reactant is chiral, as I have already taken one example and explained. So I have taken one example which already I have discussed, that in my case that in THF the major product percentage ratio was 4.3 and in another solvent tetramethoxybutane that percentage of the major product or the ratio of the major product and the minor product was 5:1. Now with respect to this value, when we are performing one more aldol reaction where two chiral components are present, then we have to check the percentage of the major product. If the percentage of the major product is more than the previous case, means either 4.3 or 5, then that will be considered as a matched aldol, and if it is less, the major product percentage, if it is less than 4.3 or 5, which already we have done, then that particular aldol condensation will be considered as the mismatched aldol condensation. Now let us take that actual example which we are considering here. Now in this case where the two chiral components are present, we have taken that Z-enolate coming from the chiral ketone, and this Z-enolate originating from the chiral ketone is allowed to react with the two enantiomer of the chiral aldehyde. So the chiral aldehyde what we are taking, that is one has the R enantiomer and another has the S enantiomer. So when R enantiomer and the S enantiomer of this chiral aldehyde was allowed to react with the Z-enolate, then it has been observed that R enantiomer, when it is reacting, that beta hydroxycarbonyl compound what we are getting, that major diastereomer has the 62% and the minor diastereomer has the 28%. Now this 62% versus 28%, this is roughly we can consider 3:1, which is less than the previous case where we have taken the only one component as chiral. So therefore this reaction will be considered as the mismatched aldol condensation. Now coming to the another part where this Z-enolate originating from the chiral ketone is allowed to react with the S enantiomer of the aldehyde, then we are getting the syn beta hydroxycarbonyl compound, but in this case the major compound percentage is 97% and the minor is 3%. So this percentage is definitely more than the previous case where we are taking the only one chiral component, means where in the THF or in tetramethoxybutane the major components percentage was, ratio was 4.3 or 5. Now this 97% is definitely higher than that ratio. So therefore this will be considered as a matched aldol condensation. So hope we have discussed the important aspects of the enantioselective crossed aldol condensation. Thank you.